Good morning, ladies and gentlemen. May I have your attention, please? Thank you. Raise your hand if you did not get red mark for today. Let's go ahead and get started. So we want to make sure that we're comfortable with differentiating logarithmic and exponential expressions. And we've seen how if we have a logarithmic expression, oftentimes it's simpler to use our properties of logarithms to rewrite our original y before differentiating. Let's see where that shows up in today's Bellwork. So number one, we'll differentiate an exponential expression, and this is a regular base e exponential. And so I'll just use my words. The derivative of an exponential function is the exponential function itself. Whole brace. Ever since exams week, we've had a little communication problem. The derivative of an exponential function is the exponential itself times the derivative of the exponent times the natural log of the base. And in this case, a base e exponential, the natural log of the base is just 1, so we don't need that at all. It looks like negative e to the negative x. Raise your hand if you have the same derivative for number 1. Negative e to the negative x. Awesome, Blossom, thank you. Let's take a look at number 2. We've seen now how we can differentiate logarithms with any base b by first using our change of base property. That is rewriting with natural log and then applying our derivative of the natural log of a function words. So here we go. The derivative with respect to m of log base 4 of m is equivalent to the derivative with respect to m of natural log of m over the natural log of 4. So this is my change of base property. It allows me to rewrite the log of any base b of an input as natural log of input over natural log of base. And in fact, we derived that last time. I remember saying we derived that last time by rewriting it with the definition of a logarithm and then taking the natural log of both sides and using our log of a power to bring down that exponent in front and solve it for that exponent. Okay, so let's go ahead and do it. The derivative of the natural log of a function is 1 over the function. It looks like we have a constant multiplier here. That ln of 4 on bottom is simply a constant. The constant is 1 over ln 4. So I'll go ahead and do the derivative of a constant times the function is the constant times the derivative of the function. And the derivative of natural log of m is 1 over m. That's pretty sweet. And so my final answer is 1 over m ln 4. Raise your hand if you have the same. 1 over m ln 4. Great work, you guys. All right. So now comes the excitement, right? We don't have derivative words for this hybrid function, right? Y equals x to the sine x. Why is that not a power function? Well, what about that original definition? Why makes it not a power function? Why can't I use my power words? Hayden? That's all right. So my power words, right? My power words work for any power function whose key characteristics would be base variable x to the constant exponent. Why is this function y not a power function?
The power is a function of the constant.
Absolutely. My exponent up there is a function of x itself. It's not a constant. Why can't I use my exponential words then? We have words to handle exponential functions where my variable is up in the exponent. What is it about this original definition y that prohibits me from using my exponential words like number 1? Megan?
Is the base is a constant?
Absolutely. The base isn't a constant, right? E to the negative x, the base e was some number, Euler's number, about 2.71828. In this case, the base is x, a variable. And so I've got variable in the base of this expression. I've got variable in the exponent of this expression. It's not a power function. It's not an exponential function. It has elements of each. So what do? Well, we don't quit. We don't throw it in the gutter. And we don't trudge through the snow to Wannabe for a field trip on the very first day to get out of our calculus example, Bellwork number 3. Instead, we go to our tool bag and we open it up. And we rummage around, and though duct tape and tattered worn it may be, we find something might help us, and that is logarithmic differentiation. So our last thing that we learned before the end of the semester was logarithmic differentiation. It's going to allow us to utilize our properties of logarithms, like in number 2, right, but in a different scenario, in order to rewrite my original and find the derivative. And so what are our steps? Well, we'll go ahead and take the natural log of both sides. And so my first step will be to take the natural log of both sides. So we'll take the log of y, and we'll take the log of x to the sine x. Now we'll go ahead and use our properties of logs to rewrite my original, namely the log of a power property. So we'll go ahead and leave the left side alone, natural log of y, but we'll grab onto this exponent and bring it on down front as a constant multiplier, right? We'll bring down that exponent as a multiplier in accordance with my log of a power property. So my rewrite is sine of x times ln of x. Step 3, now we're ready to differentiate both sides with respect to x. And so when we differentiate the left-hand side, because that's not ln of x, but ln of y rather, we have to use the chain rule, right? Because we're differentiating an expression with y in it, which is itself a function of x. So here we go. The derivative of the natural log of a function is 1 over the function times the derivative of the function. What's the derivative of my function y with respect to x? We'll go ahead and call that y prime. Right? You could also use dy dx. All right? Both are used in the AP exam. All right, the derivative of, oh goodness, what derivative words are we going to have to start out with overall to differentiate the right-hand side? So what overall words are we going to have to use to differentiate that right-hand side? Tyler?
Natural logs, like 1 over x.
Well, absolutely, we're going to have the natural log in there, but I'm saying what overall words will we have to start out with?
Product.
Product, absolutely, right? We've got x appearing in two different functions, right? So we're going to have to use the product rule. Thank you, Tyler. Let's do the derivative of a product of two functions is the derivative of the first function, so sine of x differentiates to cosine of x times the second plus the first function as is times the derivative of the second. So let's go ahead and make sure we did the product rule right. The derivative of the first times the second plus the first times the derivative of the second. And now I've differentiated both sides with respect to x. My fourth and final step for logarithmic differentiation then is to solve for y prime and substitute back in the original expression for y. So we'll go ahead and solve for y prime. That's what we wanted. And we'll solve for y prime by multiplying over both sides. So it looks like we get cosine of x ln x plus sine of x over x all times y. And what was y? Y was x to the sine x. And so if we go ahead and do that all in one step, it looks like we won't have to go gadget arm. You get everything? Yeah, it's pretty close. Great. Okay, please raise your hand at this time if you had this expression for y prime. Did you go all the way in? Yes, you did. Yes, you did. That's great news. Okay, so logarithmic differentiation is going to show up kind of today when we're using L'Hopital's rule, depending upon what function we're dealing with and what our limit expression looks like. And so you might be thinking right now, limits, goodness. Right? We haven't dealt with limits in a unit, right, since our very first unit together back in Unit 2. We started the year dealing with limits. Today we're going to be using limits again. All right, but first, let's take a look at number 4. We want to evaluate graphically. So we know in general we can evaluate a limit graphically, right, using technology. We want to go ahead and determine a suitable window, take a look at my expression, and then graphically we're going to change our window. We're going to trace, we're going to zoom, we're going to maybe use the table feature and see if there's a particular y value that the function is approaching as x gets closer and closer to my x equals c value, in this case -2. So let's go ahead and enter my original function. Goodness. I'm going to go ahead and clear out and zoom 6 to get a standard viewing window. Let's everybody go ahead and take a look. We will need our graphers later today to do some verification. So let's go ahead and take a look at my original. 2x squared plus 3x minus 2 over x squared minus 4. And I don't know what a good window is right now, and so what I'm going to do is just zoom 6 and look at my standard window, -10 to 10, and see if that's okay. So I want to see as x is approaching -2, as x is approaching -2. So it looks like -2 would be right here, so that's an okay window. I'm going to go ahead and trace. I'm going to trace, and I'm going to scooch along the function until I get closer to the x coordinate -2. And it looks like right here is -1.969696 repeating, and my y coordinate appears to be 1.2 1.244, right? 1.244. I'm going to go ahead and go past it over here on the left-hand side of x equals -2. I'm at x equals -2.27, x equals -2.1212 repeating, and my y-coordinate now is about 1.27. And so it looks to me like this function appears to be smooth and well behaved, right, as x approaches -2 from the left and from the right, and the y-coordinate that's being approached appears to be between 1.27 and 1.24, right, in between 1.27 and 1.24. Why don't I just trace -2? Let's see what y-coordinate is produced. When I trace -2 exactly, no y-coordinate is returned, right? Does that mean this limit doesn't exist? No, it doesn't mean the limit doesn't exist. It just means the function is undefined at x equals -2. The limit appears as though it does exist. In fact, I have a smooth curve. It appears that a y value is being approached from the left-hand side and from the right-hand side. It's just we have an open circle right there. It's not filled in, but the y value being approached from the left and right-hand side is the same. So the overall limit I would anticipate to exist. Let's go ahead and see if we can't find it algebraically. So we'll go ahead and scooch over our logarithmic, right, differentiation from our tool bag so it's not in the way, and we're going to sift through and see if there's something else that we could use. Find initial substitution, x equals -2 into my original expression. I'm getting 2 times -2 squared is 4 is 8, minus 6 minus 2, all over -2 quantity squared is 4, minus 4 is 0, so I'm getting 8 minus 6 is 2 minus 2 is 0. I'm getting 0 over 0. Did you guys get 0 over 0? Okay, so I have to search through my tool bag and see what might be an appropriate tool to use. So how could we attack this limit algebraically, right? How could we attack this limit algebraically? Riley E? What could we try algebraically? No? All right. Let's give them some options. How about multiply top and bottom by the conjugate? The conjugate of what? No, go on to the next one?
Yeah.
Oh, okay. Make a leaf coming down there. No? All right, I'm out of options. Go ahead and turn to your partner and let's go ahead and get some tools here. And then I'm going to come back to Riley and we'll see what's what. Enough talk. Now we eat. Okay, enough talk. Now we eat. So what do we think? What would be a good technique to try, Riley?
You could factor the top.
Yep.
And split it up and then work with it.
Let's go with that. Let's go with Riley's idea. Let's factor the top, right? And let's factor the top and then try again. And while we're factoring the top, right? While we're in our factoring mode, let's factor that bottom too, right? Let's see what comes up here. So here we got x approaches -2. We always keep our limit expression. Remember, Riley, we're looking for right around in between between 1.24 and 1.27. So let's see what we get. Top, we're factoring. So it looks like this 2x squared plus 3x minus 2. We're going to try and factor that. And it looks like this x squared minus 4. We're going to try and factor that. All right. So we'll go ahead and grab factors of my leading coefficient. That 2 looks like 2x and x are my only choices for the first. And it looks like 2 and 1 are my only choices for the last two. So I need to place those with opposite signs such that the outer and inner product sum to a positive 3x. So I'm going to probably grab onto that 2 and put it opposite my 2x to get to 4x, right? And then using my inner product of 1x, I could get to a positive 3x if I made my opposite signs like so, right? 2x minus 1 times x plus 2. Now my outer product would be plus 4x. My inner product would be minus 1x, so I'd be at 3x. Yes? Awesome. So that works on top. What am I going to have for the bottom, right, if I factor that difference of perfect squares? Sophia?
Minus 2.
X minus 2 and x plus 2. All right. Awesome, Riley. So we've got it factored. That's perfect strategy. And now we'll go ahead and notice that the top factored form and the bottom factored form share a common factor, x plus 2, and because we're evaluating a limit, and I'm not concerned with the value of that expression at x equals -2, but rather only as x approaches -2, I'm allowed to cancel those out. This is equivalent to the limit as x approaches -2 of 2x minus 1 over x minus 2. And now we'll try again. So here we go. As x approaches -2, let's see what this expression does. On top, 2 times -2 is -4 minus 1 is -5. Is that right? So I'm getting -5 on top. -2 minus 2 is -4. I'm getting -5 divided by -4, which is 5/4 is 5/4 in between our 1.27 and 1.244. Yes, it is. And so it looks like my 5/4 is reasonable according to the graph. Raise your hand if you already had 5/4 from way back a long time ago. Yes. So remember algebraically evaluating limits. Today we're going to algebraically evaluate limits too, but we're going to increase our repertoire beyond Riley's factoring strategy, beyond multiplying top and bottom by the conjugate when we have radical expression, beyond creating a common denominator to handle sum of difference of fractions. Today we're going to add a new tool, a new strategy, and that's called L'Hopital's rule. And so I'm super excited about that. In fact, they just added that to the AP curriculum this year. They just added L'Hopital's rule to the AP curriculum this year for the AB course. It's always been in the BC course. So basically, you guys are ahead of the game. But first, let's go ahead and take care of OTL number 3. At this time, please make sure that you have your name first and last. 1A. New class for everybody, 1A. OTL number 3 labeled on top. If you need a stapler, there's one on the front table, there's one on the side table. Please staple multiple pages together. You don't need to include the half sheet because there are no graphs on back. Give yourself credit for those of you who complete out of 31, please. Divide and multiply by 2. And then please box your infinite canvas score, round to the nearest half point, 0 to 2, on top. Final check is your name first and last. 1A and number 3 are clearly labeled. Please pass from the back to the front. Front rowers, we got some new front rowers. Please make sure they're facing the same direction. I appreciate your help with that. It makes it so much easier to record. Are we good with number 3, ladies and gentlemen? Okay. So, remember evaluating limits, right? Remember evaluating limits, and so we've had a variety of different strategies to be used for algebraic evaluation, right? Algebraic evaluation, multiply top and bottom by the conjugate when we have a radical expression. Factor, right? Factor and reduce. Algebraic manipulation, sometimes foiling, combining like terms. Common denominator, right? All of those were algebraic techniques. Graphically, we could use technology to investigate the behavior of my y coordinates as x gets closer and closer to a particular x value, and then see if there's a particular y value that the function values are approaching. So we've got lots of different ways to evaluate limits. Let's go ahead and do with your partner right now. We're going to evaluate the limit as x goes to 5, 4 over x minus 7 with your partner. Number 2, let's remind ourselves about multiplying by the conjugate. As x approaches infinity, right? So this is the table. Everybody find it? Everybody find it? Okay. So the first thing we're going to do is use your graphing calculator technology, right? I'm sorry, we're going to do direct substitution. So without manipulating, we're going to see what the expression equals. Then we're going to go ahead and take a look at the result from tables or graphs. So that's the numerical part. And then we're going to state the algebraic technique, right? So that's what we're going to do in a 3-step process. So my original result, when I let x approaches 5, I get 4 over 5 minus 7 So is my x value of concern 5 in my domain of the expression? It most certainly is. It looks like I get 4 over negative 2. That certainly is defined, and I get negative 2. So by golly, it looks like we're okay. Using graphing calculator technology, we could clear out my original function, and 4 over x minus 7 as x approaches 5. The y-coordinate, right, that the function it attains is negative 2. It's smooth from both sides, and so it looks like we're getting negative 2, we're getting negative 2, and our algebraic technique then, for the rightmost box, what was our algebraic technique? Direct substitution. So we were able to evaluate that through direct substitution. Awesome. All right, let's go ahead and continue then. We can kind of do these together. I want to make sure that we have time for some of the more complicated indeterminate forms. And so we'll just keep right on going. The limit as x approaches 9, so initial result, right, without manipulation first. I plug in 9, I get square root of 9 is 3 minus 3 is 0 over 9 minus 9 is 0, so I'm getting 0 over 0. Is that what you guys are getting? Great. So then from graphs/tables, let's go ahead and see my original expression. The square root of, x, close radical, minus 3, close quantity, over x minus 9. And for this one, right, if I trace 9, enter, no y value is attained. So I'm going to go instead to my table, right? I'm going to go to my table. And in my table, I've got ask. So I'm going to go ahead and choose values that are very close to, right? Very close to, but not equal to 9 on both sides. So everybody, let's choose some values like 8.9. 8.99, 8.999, 9, 9.001, 9.00, nope, 01. All right, so it looks like my y-coordinates, are they approaching a particular value from the left and from the right? And is that value the same? Yes. So it looks like here, it looks like we're thinking, right? It looks like we're thinking between 0.1666666 and between 1.666667. So I bet that's 0.16 repeating, huh? So that's probably what is a fraction? 1/6, comma, maybe? I think so too. So what would be our algebraic technique? What would be our algebraic technique for this one? Hayden?
Conjugate pairs.
Yeah, we can multiply top and bottom by the conjugate pair. The conjugate pair of the radical expression. So same terms, opposite operation. The conjugate for root x minus 3 would be root x plus 3. So let's go ahead and do that. Oh, that's not going to work so well. So let's go ahead and do that. So we're going to limit. Actually, we'll go ahead and, we already have the limit there. We're going to do it right away. Let's go ahead and do that right away. So we'll multiply top and bottom by root x plus 3. Okay, so on top, where I want all this stuff. There you go. I think I'm going to work down. I'll set up for low-key college real nicely. So here we go on top. FOIL, first outer inner last strategy for multiplying two binomials together. I'm getting x plus 3 root x minus 3 root x, no root x. That's the point of multiplying by a conjugate. Minus 9 all over x minus 9 times quantity root x plus 3. Notice how we don't want to distribute, right? We don't want to distribute on bottom. We don't want to multiply that on bottom because we're trying to create a common factor on top and bottom so that we can cancel them out, right? So now I notice that because we're evaluating a limit and x does not equal 9, we'll be able to rewrite this as one over quantity root x plus 3. Yes? And try again. So we'll go ahead and try, and we'll plug in 9 here and see if we're still have domain issues, and by golly, I get 1 over 3 plus 3. Yes! I can totally do that. Still early in the week, I can totally do that. So 1/6, which is my 0.16666 that we saw in our table. So that's pretty sweet. I'm going to do this one more time. There we go. Awesome. So what questions do you have about our number 2? So what did you guys put in the box? Did you put multiply by conjugate? The rightmost box? So multiply by conjugate. All right. This time, are we able to do direct substitution? Well, not really. As x approaches infinity, that's not a particular x value that I can substitute in the expression, right? It's not a particular x value that I can plug in like 3 and work it out. But however, I do know that with limits involving infinity, if I have a rational expression, I can consider how the degree of the top polynomial relates to the degree of the bottom polynomial. In this case, the top polynomial is quadratic, degree 2. The bottom polynomial is also quadratic, degree 2, and so I'll go ahead and compare the dominant terms on top and on bottom and construct an end behavior model. So for this, my initial would result in infinity over infinity if I could plug in an x value. Graphs and tables, oh gosh. I better do graphs and tables, huh? So my graphs and tables looks like 4x squared plus 20x plus 25, closed quantity 3x squared minus x plus 7, closed quantity. And we're trying to let x approach infinity. Yes? I think I'm going to go right to my table then, because my window, right? My window of negative 10 and 10 is not going to work. I want to choose values like 100, 1,000. So as I'm choosing larger and larger x values, right, is letting x increase without bound, what's happening to my y values? It looks like they're getting closer and closer to 1.333, yes? Yes! Okay, so what are we guessing? Yeah, oh, so 1.333, so like 4/3. Guess 4/3? All right, so what would my technique be? End behavior model, comma baby, end behavior model. Limits involving infinity. I can consider an end behavior model. And we get an end behavior model, that's my rightmost box for my technique. We get an end behavior model by considering the dominant term, right? The quotient of the coefficients on dominant term, given that their degrees are the same. So it looks to me like my end behavior model will be gained by grabbing the dominant term on top, the dominant term on bottom, coefficients included. My end behavior model then would come from a y equals 4x squared over 3x squared, which in turn would equal 4/3. 4/3 is a horizontal line, right? And so as x approaches infinity, then the y value approached is 4/3. Gosh darn it. That looks pretty darn good. All right. Sammy.
Did you say given that the degree is the same?
Yes.
If it's not the same, don't you just get like a line or something?
We do the same thing, yeah. We do the same thing. What I meant was that if the degree is the same, you can just take the quotient of the coefficients, and that's value of the limit. If the degree is not the same, you still take the quotient of the dominant terms, reduce, consider what category the end behavior model is, and then evaluate the limit using the end behavior model. Here, because the degrees are the same, we know it's going to be 4/3 without doing it, the end behavior model and all that. But yeah, good point, good distinction. Everybody good? So we're 3 for 3? Hey, that's not so bad. I'm feeling a confidence boost, right? After our 3-day weekend, coming back, getting warmed up, a little bit of snow out there. Let's go ahead and take a look at number 4. Initial substitution result in 2 minus 2 is 0 over 2 squared is 4 minus 4 is 0. I'm getting 0 over 0. So there's my first box. Tables, graphs. Let's see, x minus 2 quantity squared. Over quantity x squared minus 4, watch you use the parentheses. And now x is approaching 2, so I'll go ahead and zoom 6. And as x approaches 2, I'm getting, trace 2. No y coordinate is returned. But the function does appear to be smooth and well behaved, and so if I use my arrow keys, it looks like the y value being approached is in between negative 0.04 and negative 0.007 and positive 0.029. So in between negative 0.007 and positive 0.29, so maybe 0. Yeah. What do we want? 2, so 1.9, 1.99, 1.999. Ooh, 3 to the negative 4, so that's like 0.0003. Very small rocks. 2, error. 2.001. I gotta go 0. I'm thinking 0. Yes? Okay. Let's do it. What technique can we use? Riley, what technique might be good? Factoring, that's what I'm talking about, baby. Notice how, right, we're going to be able to factor that bottom and then see if we can't reduce common factors. Great, let's do it. So x plus 2 x minus 2. And because I'm evaluating a limit where x is approaching 2 but doesn't equal 2, then we'll be able to cancel out one of these and try again. Now I'll try with direct substitution again, and I get 2 minus 2 is 0 over 2 plus 2 is 4. I'm getting 0 over 4 equals 0. And that's what we saw. With our technique, right box? Factoring. I know we're getting close. So we've reviewed several techniques. We've had multiply top and bottom by the conjugate. We've had factoring. We've had direct substitution. My initial check here, number 5, 2 minus 2 is 0 over 0. I'm getting 0 over 0 again. Gotta go with factoring again. Oh. And you guys know the drill. If, right, the x value that I'm approaching, right, the x value that I'm approaching is a 0, one of my factors. I can cancel it out because I'm evaluating a limit. X doesn't equal 2, right? So I can cancel it out and try again. Is my x value concerned in the domain of my newly rewritten expression? Yeah, I'm getting 1/4. Are you guys getting 1/4? Okay. One more, and I do want to look at this one with graphs and tables. And so this one we will do with graphs and tables. Last one, number 5, we skirted over in the interest of time, but let's go ahead and consider what happens here. So now I've got the limit as x approaches 2 from the right of quantity x minus 3 over quantity x squared minus 4. Initial substitution results in 2 minus 3 is -1 over 2 squared is 4 minus 4 is 0. So now I'm getting -1 over 0. Is that indeterminate? No, that's not indeterminate. That's not like 0 over 0 or infinity over infinity. It looks to me as x approaches 2 from the right, my top value is going to -1. My bottom value, as x approaches 2 from the right, would be x values like 2.1, 2.01, 2.001, ensuring that this x squared is going to be slightly larger or smaller than that 4. Would x be larger? Would x squared be larger or smaller than 4 as x approaches 2 from the right? Larger, and so this is going to be a little bit more than 4. Take away 4 is a little bit positive. Why do we care? Because I get a negative over a positive. Overall, this suggests that we must be approaching negative. Let's go ahead and see. Let's go ahead and see if we get negative infinity. So here we go. My original, y equals x minus 3 over x squared minus 4. And we're letting x approach 2 from the right. So we'll go to our standard zoom 6, -10 to 10, and see what happens. Whoa! I love rational functions. So as x approaches 2 from the right-hand side, that would be over here on this branch, and it looks like my function values are shooting off towards negative infinity. So how did we do? We did okay. And what do we want to call this? We want to call this the sign test, right? When we're doing an analysis of the signs, we know that a constant over 0 is approaching infinity. To determine which infinity, though, positive or negative, we consider the signs of the numerator over the sign of the denominator. That's negative over positive. That's overall negative. And so that's how we did that. And I'll go ahead and informally call that the sign test, so I haven't come up with a better name. Sign analysis. Ooh, that sounds even better. Not like cosine. Sign like SIG, like cos. All right. So what's up? Finally, this was the moment we've all been waiting for. Direct substitution. As x approaches 1, and number 7, I'm getting 1 plus 1 minus 2 is 0 over natural log of 1. Is that undefined? No, what's natural log of 1? 0, so I'm getting 0 over 0. In graphs and tables. Quantity. X squared plus x minus 2. Closed quantity over natural log of x. Guess I don't need that. And we're letting x approach 1. I don't know what this looks like. So as x approaches 1, I have no y value returned, and yet my function appears to be smooth and well behaved. Yes, so what else could we do? And what else could we do to get a better estimate? Are you seeing what I'm saying? Yeah? So what can we do to get a better estimate?
Go to the table.
Go to the table? Let's go to our table and choose values like 0.9, 0.99. What? What are you guys getting? Are you getting the same thing? I'm getting around 3. Yes? Around 3? Okay. So, thus far we've been able to algebraically evaluate my limit expression and verify what we're seeing numerically on my table or graphically on my picture, right? What technique would be appropriate here? Factoring? I might be able to factor the top. Let's see, x. Yes. Would that produce a factor that's common on bottom? No. Multiply top and bottom by the conjugate? No, there's no radical expression. Create a common denominator? No. Sign test? No good because I don't have an infinite form. I have an indeterminate form. And so we need something else, right? We need something else. We need a new technique. And that's the point of our progression here. We need a new technique in order to evaluate this algebraically, and that new technique is called L'Hopital's rule. Super powerful. Just added to the AV curriculum this year, and I'm excited about that. So we need a new technique to evaluate this limit algebraically. Maybe. All right. That new technique is L'Hopital's rule, also known as L'Hopital's rule. Depending upon which textbook you're working with, they'll spell L'Hopital's name differently. Or I got credit for the Bernoulli brothers' work, which so often is the case in history, particularly great works of math or science. It seems like people with money always get credit. But the Bernoulli brothers did awesome work with fluid flow and thermodynamics, but L'Hopital got credit for their rule. L'Hopital's rule is super powerful. It says that if, upon initial evaluation of a limit, we get an indeterminate form, either 0 over 0. And if we get a 0 over 0, then, even if we could factor, or could create a common denominator, or could multiply top and bottom by the conjugate, we could take the derivative of the top, take the derivative of the bottom separately, and then try again. And so, if we get an indeterminate form 0 over 0, then we can differentiate the numerator, differentiate the denominator, and then try again. This is doing two separate differentiations. So it's not the quotient rule, right? It's not the quotient rule. Instead, you just do the derivative of the top. Separately, you do the derivative of the bottom, and then you try to evaluate the limit of the new quotient of the results. So if we get, as x approaches infinity, an indeterminate form 0 over 0, then we're authorized to take the derivative of the top, plus c, take the derivative of the bottom, and then try again. If we evaluate, right, our limit initially, and we get the indeterminate form infinity over infinity, we're authorized to use L'Hopital's rule. We can take the derivative of the top, take the derivative of the bottom, and then try again. So this will be super powerful, and it'll allow us to evaluate ones like number 7 now algebraically. In fact, all the other ones already got an indeterminate form of 0 over 0, or infinity over infinity too. Not having to remember the whole conjugate business, or the factoring necessarily, although sometimes it's easier too. And then lastly, something that will be very useful for us is the limit function interchange for continuous functions. That is, if my functions are continuous, then the limit of a composition g of h of x, right, can be evaluated by considering the composition of g and the limit of the inner function h of x. And so that's going to be very useful to us as well as we go to do some of these evaluations. So can we see, right, can we see what this one looks like? Let's go back to number 7. So we need a new technique. What's the new technique? The new technique is L'Hopital's rule. If we get an indeterminate form, 0 over 0 or infinity over infinity, I can take the derivative of the top, the derivative of the bottom, and then try again. Let's do that. So this technique will be called L'Hopital's rule. I'll show that I'm using L'Hopital's rule by putting a little h over my equal sign. This is the step. This is the step that I'm applying L'Hopital's rule, where I'll consider the limit as x approaches c of the derivative of the top over the derivative of the bottom, and try again. This is not something that's in the AP College Board's little h there. I'm just doing that so you see what line I'm using L'Hopital's rule, and I encourage you to do that also so I can see what line you're using L'Hopital's rule as well. If you get an indeterminate form, you have to get the indeterminate form in order to use L'Hopital's rule. We can then consider the limit as x approaches 1 of the derivative of the top and the derivative of the bottom separately, and try again. So what's the derivative of the top? Well, my top was x squared plus x minus 2, so that's just 2x plus 1. What's the derivative of the bottom? Well, the derivative of ln of x separately is just 1 over x, and then try again. So now I'll try direct substitution, and my x value of concern is in the domain of my original expression, and so I just get 1 times 2 is 2 plus 1 is 3, over 1 over 1 is 1, which is, I'm sorry, which is 3 over 1, which is 3, and didn't we get that? Through inspection, it looked like in between 2.997 and 3.0025. So how easy was that? I gotta tell you, that was way easier than multiplying top bottom by the conjugate, way easier than constructing a common denominator. And while factoring is fun, I love factoring, this is still quicker. And so L'Hopital's rule is a very powerful technique. Let's go ahead and take a look at our note sheet now. So we've got our limit as x approaches 0 of sine of x over 2x. Initial substitution, right? Always, we still do initial substitution as our first step when evaluating a limit. As x approaches 0, what happens to my numerator? Well, my numerator goes to sine of 0, which is 0, over my denominator as x approaches 0 goes to 2 times 0 is 0. So I get an indeterminate form, right? Is this indeterminate form authorize the use of L'Hopital's rule? Yes, it does. I need 0 over 0 or infinity over infinity in order to use L'Hopital's rule. It looks like I got 0 over 0, and so guess what? I can run to the hospital. I can use L'Hopital's rule and consider the limit as x approaches 0 of the derivative of the top over the derivative of the bottom separately, and try again. Let's do it. So the derivative of sine of x is cosine of x. The derivative of 2x is 2. Now is my x value of concern, right, in the domain of my new expression? Most certainly is, because my denominator is 2, right? So even if my, and 0, right, cosine of 0 exists, what is the cosine of 0? 1. And so I'm getting 1 over 2 is 1/2. And how quick was that, right? So before we couldn't do anything with this, and now we can do it in one step, so that's pretty sweet. Let's take a look at another. The limit is x approaches infinity of e to the x over x squared. As x approaches infinity, right, what happens to my exponential function, y equals e to the x? Well, that approaches infinity, right? So that's over here, the right-hand behavior. And as x approaches infinity of x squared, right, what does y do as x approaches infinity? Well, that's also going to infinity. Okay, so I'm getting infinity over infinity. Right? I'm getting infinity over infinity. Is that an indeterminate form? Yes. Does it authorize the use of L'Hopital's? Yes. And so I need 0 over 0 or infinity over infinity in order to use L'Hopital's. Before we do, I want to think a minute though. E to the x over x squared, which of those functions, both of which are approaching infinity, which one do you think approaches infinity more quickly? That is, which one do you think wins, grows more quickly? E to the x, x squared. Now's the time for that borderline school inappropriate Super Bowl beer commercial from the 1990s, right? Tastes great, less filling. E to the x, x squared. Well, before we get into a knockdown, drag out shouting match, right, we can consider, right, e to the x is an exponential function, right, that grows exponentially versus x squared is a quadratic function, a power function. In the long run, an exponential function will always win out over a power function, right? If we're talking about exponential growth. And so, gotta say the top's gonna win. If the top grows to infinity more quickly, it's gonna overwhelm the bottom, right? And so I'm gonna get overall infinity as my guess. Let's see. I get infinity over infinity, which authorizes the use of L'Hopital's. You always must show that, do the check. And now let's go ahead and use L'Hopital's rule. We're gonna go ahead and consider the limit as x approaches infinity of the derivative of the top over the derivative of the bottom. So what's the derivative of the x? E to the x, what's the derivative of x squared? 2x. And try again. As x goes to infinity, where does the top go to? Infinity. As x goes to infinity, where does the bottom go to? Infinity. Usain Bolt. It's going up. We'll take you to Rio 2016 Olympics. We'll see if we get any Usain Bolt poses. All right, so what can I do? Take the derivative again of the top, take the derivative of the bottom separately, and try again. I've got an indeterminate form that authorizes use L'Hopital. So I'll show that again. So e to the x differentiates to e to the x. 2x differentiates to 2. Try again. As x goes to infinity, what does e to the x do? It goes to infinity. What does 2 do? It goes to 2. The limit of a constant is the constant itself. So that's just 2. Is infinity over 2 an indeterminate form? No, it most certainly is not indeterminate. We can determine the value of that limit. As x approaches infinity, we see that that is going to infinity as well. So this is infinite, and it's infinity. And remember, we can say equals infinity, even though infinity is not an actual number, right? This limit does not exist. It's said to be infinite. However, by saying that it equals infinity, describes exactly the manner in which it does exist. We know that graphically my y values would increase without bound as x goes to infinity, as x increases without bound. That's pretty sweet. Okay, so we can, the point of this one is we can use L'Hopital's rule multiple times as needed, so long as we get an indeterminate form 0 over 0 or infinity over infinity. Let's consider the next. So as x goes to 1, then 1 minus ln of x would be, is that 0? Right? 1 minus ln of 1 is 0? No, that's 1. And then 1 minus ln of 1 minus 0 is 1, yes? All over 2 times 1 is 2 minus 1. So I'm getting 1 minus 0 is 1 over 2 minus 1 is 1. Is this an indeterminate form? No, right? Can I determine what the value of this limit is? Yes, it equals 1 over 1. In fact, 1 is in the domain of my original expression, so I can evaluate this through direct substitution. The point of this is do not start differentiating blindly, right, top and bottom, because we're in the section called L'Hopital's rule, where we take the derivative of the top over the derivative of the bottom and try again. If direct substitution results in a value or a form that we can evaluate, then don't, right? We're not authorized to take the derivative of the top. In fact, we're not going to get the same thing here. So we have to have an indeterminate form 0 over 0 or infinity over infinity, and that's the point of this one. All right, let's see what happens as x goes to infinity. Natural log of x, though grows slowly, does approach infinity as x goes to infinity, right? It just takes a long time, right? And so on top, I am getting infinity. On bottom, I've got the cube root function. The cube root function is my serpentine S-curve, but it's sideways, right? And so as x goes to infinity, then this one also approaches infinity, but also slowly. So now if we had to guess who's going to win out here, again, I've got infinity over infinity. Who's going to win? Who approaches infinity more quickly? Well, in the same way before, when an exponential, right, function, exponential growth, won out over a power function, remember that a logarithmic function is an inverse of an exponential function, right? And so I'm thinking that now the power function is going to win out over ln of x. Okay, so maybe 0. I don't know. We'll see. So what can we do if we have an indeterminate form? We can take the derivative of the top, take the derivative of the bottom, and try again. So because we have an indeterminate form that authorizes the use of L'Hopital's, we'll go ahead and consider the limit as x approaches infinity of the derivative of the top over the derivative of the bottom. Shoot. What rule will we use on the bottom? Power rule. Right? Power rule. That's really x to the 1/3, whose derivative is exponent times the base raised to 1 less. But we're doing this separately. This is not x to the negative 1/3 starting out. We're taking the bottom and considering it as a function on its own and differentiating separately and putting it on the bottom. So we're doing the derivative of x to the 1/3, which is 1/3 x to the 1/3 minus 1 is negative 2/3. What is that we're getting? Negative 2/3. What? No idea. So I'm not going to the hospital right now. All I'm doing is going to rewrite this expression. I'm going to rewrite this expression. 1 over x on top is the same as an x on the bottom. a 1/3 on the bottom is the same as a 3 on top. And x to the 2/3, negative 2/3 on bottom is the same as x to the positive 2/3 on top. So all I'm doing is I'm rewriting this expression by hopping the line and changing the sign on this denominator power. A reciprocal, right? A reciprocal 1/3 on bottom is equivalent to a 3 on top. This 1/x is the same as an x on bottom. Also that I can rewrite this yet again using a quotient of powers property. It looks like this is x to the 2/3 over x to the 1st. This would end up being x to the 1/3 on bottom. And as x goes to infinity, right, as x goes to infinity, then this denominator, right, this denominator will go to infinity slowly. So I'm getting 3 over infinity. Is that indeterminate? Right, is 3 over infinity indeterminate? No, it most certainly is determinate, and it looks like it's going to shrink towards 0. So this one we were able to evaluate. It took a little bit of work, but we got there. Right? It took a little bit of work, but we got there. That's very sweet. Okay, so let's go ahead and consider as x approaches pi from the left-hand side. As x approaches pi from the left-hand side. What I want you to do is go ahead and try this one with your partner. Right? Start with direct substitution, and then we'll come back together and we'll check. If you have questions, catch my eye as I'm coming through the aisles.
Yes.
Okay, ladies and gentlemen, let's come together and share our findings. Are you getting an indeterminate form? No. So we don't need to take the derivative of the top and the derivative of the bottom. In fact, we're not allowed to, unless we generate, upon initial substitution, an indeterminate form, 0 over 0, or infinity over infinity. Those are the only two forms that authorize the use of L'Hopital's rule, that authorize the use of taking derivatives on top and bottom. And so, upon initial substitution, I'm getting the sign of a number approaching pi from the left-hand side. Well, sign of pi is 0, so I'm getting 0 on top, over, as x approaches pi, cosine of pi is -1, so I'm getting 1 minus a -1. 1 minus a -1 equals 2, and so initial substitution results in 0 over 2. Is this indeterminate? No, this exists and equals what? 0, and so this is just 0. Raise your hand if you had 0 for this one already. 0? Way to go, you guys. Awesome. And now, it's that special time. No. Yes. Not that time, Riley. Not that time. It's time for everybody's second favorite game. Am I indeterminate or not? What? Am I indeterminate or not? Round 1. So this is how it works. Am I indeterminate or not? Ready? Consider, right, a quantity approaching 0 over a quantity approaching a constant. And so consider the quotient a quantity approaching 0 over a quantity approaching a constant? Am I determinate or indeterminate? Determinate wins. This is oh, goodness. This is determinate, and what would it equal? We can determine this to be 0 here. Let's flip it around. Round 2. What if I had a quantity approaching a constant, right, over a quantity approaching 0? Am I determinate or indeterminate? Determinate, right? This is an infinite form whose value will be positive or negative infinity depending upon a sign type. So this will go to one of the infinities. Right? This will go to one of the infinities depending upon the sign type. So that's certainly determinate. What about a quantity approaching infinity over a quantity approaching a constant? Determinate or indeterminate? Kyle? Determinate. We can determine this value, right? I know that it's going to go to the one of the infinities, again, depending upon the signs, plus or minus infinity over plus or minus constant. Positive or positive is positive, positive or negative is negative, and so on and so forth. And so this is going to go to one of the infinities as well. Good job. What's 10? Are you the only one on the board? Nice. Keep track of that. It's going to come in handy later. Yeah. What about
2 points.
a quantity approaching a constant over a quantity approaching infinity? Determinate or indeterminate?
Determinate.
Determinate, right? This is definitely determinate, and we saw how this is going to shrink towards 0, right? It's going to shrink towards 0. So this is determinate and it equals 0. Awesome. So then which ones are determinate versus indeterminate? Well, remember 0 over, oh boy, I just took my 0. 0 over 0 is indeterminate in an authorized L'Hopital's rule. And lastly, did you get one more? Nope. And what's the other one? Infinity over infinity is the other indeterminate. Okay. So we need 0 over 0 or infinity over infinity in order to use L'Hopital's rule. Right? We have to have those in order to use L'Hopital's rule. Okay, but that's not all. So quotients are easy, but that's not all. We also have to consider summary differences. So if we consider infinity plus infinity, right? Infinity plus infinity, is this determinate or indeterminate? Determinate or indeterminate? This is determinate. If this quantity is approaching infinity and another quantity is approaching infinity, I'm adding these two infinitely large quantities together, then overall this is determinate and it equals, well, it's infinite, I should say. Right? So we can determine that that's approaching infinity. No problem. The problem is if we have a difference. So our indeterminate form is a difference involving infinity. If I have infinity minus infinity, this is where we are indeterminate. What? All right? Why are we indeterminate here? Isn't that just 0? Well, it depends. If that first quantity is approaching infinity more rapidly than the second quantity, that is, I'm getting a larger and larger number, subtracting off a large number but not as large, the result could be infinity. What if the reverse were true? What if that second quantity were approaching infinity more rapidly than the first? If this second quantity is approaching infinity more rapidly than the first, it's going to overwhelm that first term, and I'm going to drag the overall expression down towards negative infinity. And that's why this is indeterminate. And so we've got an indeterminate form now that's an indeterminate difference. And so we've got quotients, 0 over 0, and infinity over infinity. And we have a difference, infinity minus infinity, okay, is indeterminate form. The last thing we need to add are powers. Our powers and a product. So what about a product? Well, is 1 times infinity determinate or indeterminate? Determinate, right? Determinate. If 1 times infinity, right, an infinite quantity here, whether positive or negative, is going to go to 1 in the infinity. So that's certainly determinate, and that's going to be infinite. And let's cut right to the chase. What about a quantity approaching 0 times a quantity approaching infinity? Well, would it be nice, right, if this were just 0? Because 0 times anything is 0. But the problem is that
Oh, it's approaching 0.
this is a quantity that's approaching 0 times a quantity that's approaching infinity, right? And now we get into that whole game. Who's growing more quickly? Who's shrinking more quickly? Considering the growth of e to the x versus x squared. Consider now how quickly this quantity is approaching 0. If that first quantity is approaching 0 more rapidly than the second quantity is approaching infinity, it's going to win out and pull this overall value towards 0. However, if the second quantity is approaching infinity more rapidly than the first quantity is shrinking, it's going to win out and trying to pull the value towards infinity. What's more often the case than not, however, is that there's some balancing point, and it ends up being something like 5/4 or negative 2/3, right? Okay, and so oftentimes there'll be some balancing point in their growth, and we'll use that during what we call rule. However, we'd have to rewrite this in such a way that we get it in indeterminate form. So this is indeterminate. So we've got a product, we've got a difference, and we've got two quotients. The last thing then are our powers. So our powers are tricky. Our first indeterminate form is 1 to the infinity. And right now you might be thinking, if I take 1 and I multiply by itself an infinite number of times, the result will be 1. To which I would reply, yes! But remember, we're evaluating a limit, and we'd be considering a quantity that's approaching 1, being multiplied by itself an infinite number of times. And so what I want you to do is to consider if we were approaching 1, but from the left-hand side. These are values of, that's like 0.9, 0.99, 0.999. If I multiply 0.9 by itself over and over, what do I get? Yeah, 0.9 times 0.9 times 0.9. What's happening to those values? They're shrinking and being pulled towards 0. What happens if x is approaching 1, but from the right-hand side? Numbers like 1.01. Whoops. Right? If I take numbers like 1.01 and multiply by itself over and over again, what's going to happen to these values? Well, these are getting bigger, and so this is trying to pull it towards infinity. This is trying to pull it towards 0. So we've got a battle going on. And again, this is an indeterminate form. So indeterminate 1 to the infinity is indeterminate. What else do we have? 0 to the 0, right? 0 to the 0 is an indeterminate form. Why is 0 to the 0 indeterminate? Well, we think that anything raised to the 0 power, right? Anything raised to the 0 power is equal to 1. And that's true. Any non-zero number raised to the 0 power is equal to 1. But again, we're dealing with a limit. A limit where this base is approaching 0, right? Where the base is approaching 0. So here we're getting things like negative. If it's negative, right, 0.0000, then we've got a situation, where my exponent here is 0. That comes from the fraction where my exponents are equivalent, and I have a 0 on the bottom of a fraction, and we can't evaluate that. And so 0 to the 0 is an indeterminate form. 0 to the 0 is an indeterminate form. Awesome. And lastly, we have infinity to the 0 power. So infinity to the 0 power is going to be our final indeterminate form. If it were 0 to the infinity, that would be fine, because I'm multiplying a smaller and smaller quantity over and over and over again, right? That's going to shrink towards 0. But infinity to the 0, if my base is going to infinity more quickly, right, then it's trying to make this overall value larger and larger. If my exponent is shrinking towards 0 more quickly, it's going to try to pull the overall value to 1. All right, so this is our final indeterminate form. All right. So let's go ahead and, without further ado, get down our indeterminate form. So everybody on our note sheets, we've got our indeterminate quotients, right? Our indeterminate quotients, these authorized use of L'Hopital's, they include 0 over 0, and infinity over infinity. We have a single indeterminate product. Our indeterminate product is 0 times infinity, right? 0 times infinity. We have a single indeterminate difference. That is infinity minus infinity. And we have 3 indeterminate powers. And so our 3 indeterminate powers, we've got 0 to the 0, infinity to the 0, and 1 to the infinity. Which of all these indeterminate forms authorize the use of L'Hopital's rule? Only the first two. Only the quotients authorize the use of L'Hopital's. And so these are the only ones that authorize the use of L'Hopital's. So my job becomes rewriting these other indeterminate forms such that they are a quotient, 0 over 0 or infinity, in order to apply L'Hopital's rule. Let's do a couple together, and then it looks like our new schedule, we end at 9:40, right? At 9:40, and so we're going to have to come together fairly soon for closure. So let's do an example together. Here's another indeterminate form. Everybody find your other handout. As x approaches 0 from the right-hand side, what does natural log of x do? So we're always doing initial substitution first. Well, as x approaches 0 from the right-hand side, natural log of x goes towards, I'm trying to hold it, negative infinity, right? Negative infinity. Minus the natural log of sine of x. As x goes to 0, right? As x goes to 0 from the right, sine of x would be approaching 0 from the right, which means that ln of a quantity approaching 0 from the right is also negative infinity. So I'm getting negative infinity minus negative infinity. What? Well, that would be negative infinity plus infinity, and this would, lo and behold, be an indeterminate form. This is my indeterminate form, my indeterminate difference, infinity minus infinity. If this first infinity is growing more quickly than the second, it's going to win the tug of war and pull the overall value of the expression towards infinity. If this second infinity in the subtraction here is growing towards infinity more quickly, it's going to win the tug of war and pull the overall value of the expression down towards negative infinity. Or is there some balancing point, some break-even point, and a constant is approached that we can evaluate algebraically? We shall see. So what can we do? Fresh out of ideas. What's that? Could we use log props? Let's see if we could use log properties to rewrite this. So Riley recognizes that we have a difference of individual logs. Yes, Riley?
Yes.
So let's go ahead and rewrite this as a log of a quotient. Let's do it. So we'll go ahead and rewrite this as the limit as x approaches 0 from the right. And we'll condense that using log properties. And we'll rewrite this as the natural log of, and it's going to be first term over second input. So I'm getting x over sine of x. Is that what you guys are getting? Awesome. Let's try again. As x approaches 0, x goes to 0, and sine of x goes to 0. I get 0 over 0. So I'm getting an indeterminate form in here. Right? I'm getting an indeterminate form over here. However, I'm asked to evaluate the limit of the natural log of 0 over 0. And so what we're going to do is use the last thing on your sheet. Right? Underneath corollary number 2, the function limit interchange theorem. This will allow me to consider the limit of this composition of functions as the function of the limit of the inner function. What? We're going to interchange the limit in this natural log. We're going to rewrite this as the natural log of a limit using the function interchange theorem, which is super powerful. So we'll rewrite this as natural log of limit as x approaches 0 from the right of x over sine of x. All right, guys. In the interest of time, we're going to scooch, scooch, scooch. As x goes to 0, top goes to 0, bottom goes to 0. I get an indeterminate form. Does this indeterminate form authorize these L'Hopital's? Yes, so from the inside out, we'll keep my element on the outside. We'll take the derivative of the top. 1 over the derivative of the bottom. Cosine of x. And we'll try again. As x goes to 0, cosine of x goes to 1. Okay. So this whole limit expression is just 1. So I'm left with the quantity approaching ln of 1. What's ln of 1? 0. Who won? There's a balance. In fact, x and sine of x behave very similarly as x gets close to 0. So this ended up being about the same rate of infinity as the same rate of infinity balanced out and got 0. Okay, guys, our closer today asked us to list the indeterminate forms. We can do it. I believe in you. 3 minutes, no problem. So what does it mean to be an indeterminate form? What are the indeterminate quotients? What are the indeterminate products? What are the indeterminate differences? What are the indeterminate powers? Which indeterminate forms authorize the use of L'Hopital's rule? Nice. And how do we apply L'Hopital? So let's go ahead and get a written response for each of these. Tyler. No, we're going to do one more of them tomorrow. I mean, yes and no. Yes, you should. I think we're going to do one of them with indeterminate powers, but I think it's not number. I think it's until number 4. Is it? What's the one with x to the sine of x? Or we're going to do number 4 together. No, don't do it, actually. Don't do it. Don't do it. Okay. So we can evaluate through initial substitution, right? Just by looking. Quotients, 0 over 0. Infinity over infinity. Indeterminate product, 0 times infinity. Indeterminate difference, infinity minus infinity. And 3 powers, what? 3 powers. 1 to the infinity, 0 to the 0, and infinity to the 0. Which indeterminate forms authorize the use of L'Hopital's rule? Only 0 over 0 and infinity over infinity. How do you apply L'Hopital's rule? Take derivative of the top, take derivative of the bottom separately, try again. Not the quotient rule. Okay, ladies and gentlemen, nice job today. Yes.